So let me just so the goal for today is just to give you an overview of data mining field. What the first thing before we define the field scope, let me first define what is data mining. So many people say data mining is statistics, a lot probability things. But there's a fundamental difference between data mining and statistics. So the first difference is if you look at, if you train in statistics, you have built a statistical model, you know that in the statistics you have a lot of equations. Basically you are running linear equation, you are running a functional form. In the functional form, you have to make assumption about certain functions. But in machine learning, there is no functional form. So typically, either you try to maximize the margin, separating two classes, or you do something else. But there's no assumption on what is underlying functional form. So that removes that makes machine learning is more adaptive to many different kind of domains, to more unstructured domains that you don't have a functional form to characterize the data. Secondly is in traditional statistics, so people use MATLAB, people use R to run a model, build something interesting, predictive model. They seldom care about the speed in the real time or in the computational training time. But in many real applications, we care about the time. We care about first of all, the training time. We need to quickly turn around. Secondly, in the this chair here. So the quickly we also need to be able to deploy in the real time for streaming data for a lot of environment in the real time decision. So the speed is very important for data mining. That's why we care about speed. And thirdly is data size. So people talk about in traditional machine learning, people talk about maybe hundreds of thousands of data points. But once you come into commercial setting to large data, you talk about terabytes, petabytes of data. Every day, like for eBay, we have about 10 terabytes of log data. We have 5 terabytes of listing data. So all those data has to be processed. Now Google, Yahoo has even more data. So that the data size create a lot of challenge. First of all, how do you do processing? That's where Hadoop, all the big data infrastructure comes in. And then how do you do the machine learning on such a big data? So and also data size gives you more power to make your model better, to give you more precision, more accuracy. Like if you look at Google's translator in the last 10 years, keep improving because they get much more data now comparing to traditional machine learning translation study. A fourth difference is the wearable size. So typically in we did the stroke study. In the traditional medical domain, when they predict stroke, you look at maybe 30 wearables. So patient blood pressure, glucose, cholesterol. So there's a lot of doctors has knowledge in this field. So they say these are the 30 most important wearables we care about. Let's use this wearable to make prediction. It turns out that with machine learning method, we can handle way more number of wearables. So for example, in our stroke study, we take about 200 wearables on survey data. So basically, the survey data look at a patient and say, did you walk today? How much salt did you take? There are many questions you can ask beyond what doctor originally thought. So by throwing in all different wearables, the machine learning model was able to, so our model, we showed that with more wearables, we have a more predictive power than the traditional model. Secondly is now with bioinformatics, with hundreds of thousands of genes, with many, there is with many variables, but a very few number of data points. How do you build prediction in that sense? So that is another way that machine learning fundamentally different from a traditional approach is is being able to handle very large number of variables and also automatically select the important variables. Any questions so far? Okay.
But I'm just curious, I mean, just in terms of definition, I mean, aren't the people in statistics, aren't they also using machine learning algorithms and tools as well themselves?
If they work on machine learning problems, right? I mean, traditional, when I'm comparing so-called traditional statistics, I'm talking about in 80s, 70s, what people do linear regression or least square, those are what I'm comparing to. Yeah. Now, certainly nowadays, the new statistician probably move into machine learning field. The second part is how is data mining comparing to machine learning? Just the term. So people basically, essentially, it will become clear in a couple slides later. So I would say machine learning is a subset of data mining. So data mining probably also include the big data infrastructure, include the stream mining, including recommender system. Recommender system not necessarily use machine learning. So machine learning basically means supervised, unsupervised learning, a learning model, how to build a model. But the data mining is much broader. You can say I apply data mining to stream data, to social network, to different kind of domains. So data mining has basically a larger scope, and also people care about the size of big data in data mining field. If you go to machine learning conference like ICML conference, the algorithm, the focus is more on the algorithm side. But if you go to data mining conference like a KDD conference, the focus is more on the industrial applications. So that's the still slight difference between these two communities. And just quickly motivated this talk, but I will transition to the more deeper high-level overview. So examples of data mining, certainly people look at Amazon when they say frequently bought together, here's what other people already got. That's part of the data mining paradigm. We call that frequent pattern mining. They mine the patterns. And secondly, like in the Netflix, when we do movie recommendation, that's part of data mining. On the text mining side, people, when you type anything in the search engine, how are they able to do a search suggestion? That's also mine the search data that people have done before. In the genome study for 23andMe, by the way, how many of you did your gene test? Cool, I did mine. So it's $99. You can send in a sample, saliva sample, and then they give you back your ancestor information, about 20 kind of disease you are prone to, and other kind of, how addicted you are to coffee or something like that. So, which is pretty cool. But they are the largest. Right now, they're accumulating the data, I guess more than any hospital, more than any university institution. They are accumulating data about the individuals. So they have gene data about everyone. And hopefully what they can do is mine correlation between genes and a certain disease. Because given such a large population, we can find out how likely certain gene would cause a certain disease. Before, because sample is too small, there's no conclusive answer for that. And certainly do like in the heart monitoring in the real time, how to detect that there is abnormal action in the heart. That is another thing data mining can do. So I want to basically cover, basically the point of this whole slide is going to say, here's the major topic we talk about in data mining. Now the fundamental part is the methodology part. Frequent pattern mining was machine learning. Frequent pattern mining was actually started in early 90s, but at that time it's called a mining pattern from database, from data warehouse. And that's the story. People heard about the bear, the diaper and the bear story. right? So that is mining the, have you heard about that story? Okay, so I retell the story again.
Diapers and beer. Yeah, why did the person buy diapers and beer?
Yeah, so in the store, in the grocery store, what they found is people who buy, there's a young father who at Friday evening, they go buy diapers, but they also pick up beers when they buy diapers. And they found that there's this frequent correlation between buying diaper and beer. So the manager decided to put beer next to diaper, and then the sale of beer just went up. So this is a story about the frequent purchase pattern. Two things are purchased together. How would that help you to change your shelf display, to change your inventory planning, to change how to correlate different products? So that is frequent pattern mining. So that developed in a very different discipline. It's more in the, we call that traditional data mining discipline. But then they merge very quickly with the machine learning. Machine learning, it has different origin. It came from the artificial intelligence since the 1950s when people built the neural network, when people try to build machines that can think, can behave like humans. So that was a very different discipline, but then they now totally merged together. So in the machine learning, we have supervised learning, more like a classification, classify something good or bad, like spam, whether it's a spam or not spam. If you want to predict whether a salesperson, the sales response from a customer, whether that person would respond or not, or you want to predict a loan, whether it's risky or not. So that's a binary classification. In the unsupervised setting, there are a lot of situations you don't have a class, you don't know good or bad, but you know, like online, people talk about different topics. So how do we group the topic together? So each of these domain has a lot of research, a lot of applications we can talk about. Besides that, another topic is recommendation system, personalization. People talk about Netflix, talk about mobile recommendation, online advertising. There are many ways you can apply a recommendation system, and it has its own methodology, its own technique. The second domain become very popular is network mining or graph mining. Graph mining actually started with Google on the page rank. So if you think about the whole internet, it is a graph. Every page is a node, and then you have a link going out to other nodes. If you look at how do they do page ranking each page, is look at the number of links essentially coming back to this page, right? So you have to traverse from your current page to the link and then back and see how many total links you essentially converge to this page. That give you a ranking score that they call the page rank score. So that score would show you how important this page is, and that allows you to rank different page. Now with the social network, with Google, Facebook, Twitter, LinkedIn, we certainly can mine the connection between people, connection between maybe articles, there are many ways you can mine the relationship. Streaming data, it now becomes more and more important. For example, in the data center, each computer has a lot of traffic requests. How do you monitor the data center, the health of the server? How do you see whether there's abnormal activity or intrusions? Or intrusion detection is part of a very important topic people talk about. And then just on web traffic, if you have an internet company, there are a lot of people request your page today. Maybe there's an attack. You don't know whether it's a normal request or it's a malware attack on your server. So there's a lot of things to study there. Text mining certainly is a very big domain. All the data on the internet, from blog to Twitter, to tweets, to Facebook discussion, to company customer survey, to you can think about the many text data. Basically, essentially, that's how we human communicate with each other. So mine those text data, extract information automatically. It's also very interesting. And finally, there's a lot of research on image data, video data mining, because now video camera becomes so inexpensive. You can, with less than $150, you can buy a IP camera setup at your home, and you can record. They have a real-time recording. You can watch that on the internet, see what's going on in your home, and that they can also save up to 30 days of your video data. Then they also offer automatic event detection, meaning suppose you have a cat runs around, so then the system. So for example, if you want to go back to watch to see something going on not yesterday, but it's 24 hours, you cannot sit there and watch 24 hours, right? So the company provide the event detection. They say at this moment there's some event, some activities, and in order to do that, they have to do some the video mining. So video mining also, suppose they're smarter, they can say, oh, there's a party at this time. You can check in this hour, or there's a gathering, there is another special event. So if you go back to 30 days, you don't have to check every hour. That's the intelligence in the video mining. So all these domains actually use the methodology I just talked about in the top. In the stream mining, you can use frequent pattern mining. You can use supervised learning. You can use clustering. So there are different ways to understand the data. So each of these basic methodologies still can apply to each domain we just talked about. The infrastructure side is big data. So big data is basically it's how to move the data, how to process data, how to speed up the computing. Like Hadoop is one solution, and then there's parallel computing. There's this massive MOA. How many of you are using MOA? Okay, MOA is called a massive online analysis. So how many have used Weka? Okay, all right. So we have some people use Weka. Weka is Java-based. MOA is also built by the Weka group. So Weka is done on PC. It's offline training, but MOA can be done online. They can process a massive amount of data, give you training, online training samples. So those are the solutions for big data we will talk about. And finally, if you are building a team, or if you want to join a company, either way, what's the requirement for being a data scientist? How do you build it? What's the profile people are looking for? How should you build the data science team? So we look at the different qualifications, the basic fundamental knowledge a person needs in order to do the data science. Any questions so far?
Can you explain the difference again between the supervised and unsupervised? What
I'm going to.
Oh, labeled and unlabeled data.
All right. So the first, so the explanation here, I will have slides to talk about supervised versus unsupervised, but they give you high-level separation between supervised and unsupervised. Inside supervised, we have classification, which means you can have binary classification, 2 different classes, or you can have many classes. For example, there are 18,000 product category on eBay. That's the number of class we have. So that's binary. That's multi-class classification. You still do classification on that. The regression is traditional, mostly the statistical method. However, with machine learning approach, the decision tree can be used for regression. SVM can be also used for regression. So the traditional classification method can be also adapted to regression situation. Even neural network can be applied to regression. In the unsupervised learning, these are the 3 clustering methods I mentioned. So what's the main difference? What's the fundamental difference between unsupervised versus supervised is you in the supervised setting you have some data that's labeled by human. So basically they tell you use the example for the for approving a bank, try to approve a loan to the customer. So I look at my current customers who default on the loan, right? And those who haven't defaulted on the loan. So I have labeled data, people who are risky, and the people who are not risky. That's the label I have. And then I have a description about all the customers. So that is called supervised learning. I can use that data to build a model to say who is risky. So how should I decide on the loan? Now the unsupervised setting, there's no human labels. As I said, so suppose today you want to go out to Twitter, say, I want to find out what's the top 10 topics people talk about today. So there's no one tell you what are the top 10 topics. Basically, you have to look at all the important discussions, like highly popular words, and then group them together and say, here's maybe politics under certain topic. People talk about or sports. People talk about certain things. So those are the unsupervised learning we talk about. All right.
So I can make a comment.
Yeah.
At a high level, unsupervised learning means unconstrained. There's no constraint. You can do anything. And supervised means you're just in constraints basically. For example, if kids are playing, you give them a sandbox, play with the sandbox basically. That's supervised learning. Unsupervised means there's no constraints. And no
constraint. The word constraint means different things in different domains.
Labeled and non-labeled data.
Yeah.
So
easy way just say labeled or not labeled.
No, basically you're learning within a boundary. You're given outer boundary. You're learning within that. Are you giving training, for example? You train your algorithm with prior data.
The unsupervised, like DB scan, LOF, k-means, it means that you don't know. You're trying to discover what the clusters or the groups are. You don't have labeled data yet. So typically the way to differentiate is supervised. You're working on labeled data that has tags, labels, whereas the unsupervised you don't. You're trying to discover.
Okay. Because today is just high level, we won't be able to go into examples. But when we come to suppose we have a session on clustering, we will go deeper into that. Now, what's most interesting, people keep hearing about neural network, decision tree, SVM stuff. So this just give you a timeline on how are those algorithms invented and how they're used today. The earliest is a perceptron model in the late 1950s, early 60s. So that is a model. Basically, there's no hidden layer, just the input node to the output node, and people quickly discovered that. But it's very exciting at that time. People say we can model the neurons, how neurons work. With the input, we can create some function, and the output is a function of the input. It turns out without a hidden layer, the simple output, there are many functions cannot be represented by neural networks. So people were quite disappointed after Minsky wrote that article criticizing neural network. So for the whole 10 years, there's no research on neural network. But then in 1980s, people find that suppose we add a hidden layer, then neural network can become very powerful. It can actually represent any function. You can have not just one hidden layer, you can add 2 hidden layers. So the neural network becomes very useful to almost predict anything. Still today, if you use a credit scoring agency like FICO, they actually still use a neural network to do credit scoring. So it's been used in the financial industry, used in insurance industry, and still being used by some industry today. But the problem with neural network is the training is very slow. So it's an online learning method. You feed one examples and look at the output, comparing to the ideal output, you propagate the error back, and then look at the second example. So you keep feeding examples one by one instead of doing the whole batch learning, look at the whole population. So that give rise to other algorithm that we call batch learning. Batch learning basically you take all the negative example, positive examples, and look at the difference. Look at the so in decision tree you are trying to build a tree. I will explain the actual algorithm later. So decision tree was invented in 80s and going very popular in 1990s. And then later SVM was invented in mid-90s, become very popular for the next 10 years. The current most popular method is logistic regression, which is a very simplified kind of generalized linear regression model. So it fundamentally is a linear model. It doesn't have the so-called higher dimensional power like SVM, but it's very fast and used by most internet companies from Google to Yahoo, eBay. Basically, logistic regression has it's just because of the speed. Secondly, it's because now we have so many data, so how the accuracy of logistic regression can approach very quickly to the SVM can achieve.
I have what
Yeah.
what are you conveying with your dotted lines there?
Dotted line means just being used, but not used so heavily.
Since logistic regression uses fuzzy logic.
No, I will show, actually I have a slide on logistic regression. So logistic regression is just a function. Basically it says I map input. Input is, the actual input is x. So you have a linear function of x z.
Okay.
And then you convert z to this logistic function.
Okay.
And the function, the value of the function goes from 0 to 1. So essentially, it's nice to say I have 0.95 confidence that this is going to be class 1, right? This is going to be positive class. So if your y is a number, the number is prediction. So if y above 0.5, you say I predict this positive class. Is below 0.5, I predict this negative class.
How many features we can detect? Maximum any there is any limitation like
There's
1,000,
no limitation.
10,000?
That's what's nice about. So if you look at the linear function here, the n can be any number.
Okay.
Yeah. So you can logistic regression is a linear, transform the linear function, transform into this logistic form.
Computation wise, is it easy?
It's not easy. Actually, traditionally for more than 20 years, basically before 2003, 2004, the traditional in the statistical community, the computing of logistic regression is very slow. And even today's package, certain packages are very slow in doing logistic regression. But there's a PhD thesis come out in 2003. Basically, it's in the computer science department. They invented a way to speed up logistic regression. So then later there's several papers coming out to help us to quickly find a solution with mostly gradient descent method, with more search method, not the closed form solution, but they can give you a solution much faster.
But it is popular these days.
Yes, yeah, those are already in packages available. Like for Python, if you use Python for scikit-learn, there's a logistic regression there.
What do you mean by parallelizing?
It can be parallelized too. So in Yahoo, in Google, they all internally have a parallel version of logistic regression running.
So it's not like 10 logistic models can run together to predict something else.
You split the problem up into pieces, and then you work at the same time on each piece.
Yeah. So let me go back to, so this is a timeline about the 4 major algorithms. Certainly there are many other algorithms like deep learning. Deep learning basically is a continuation of a neural network, but adding on top of neural network, the multiple neural network together, what they can do. And then there's other machine learning model. Basically every year there's a new machine learning model invented. So I just picked the 4 major ones that people use today.
So Bayesian network is a part of decision tree or is not?
No, Bayesian, so I didn't mention Bayesian here. Bayesian, you can think about it as a graphical model. So because in Bayesian network, it's a node with the connection between nodes and the probability propagation. So it's a graphical model. Our problem with Bayesian network is because it's a graphical model, the propagation takes a long time. So it's mainly computational speed we worry about. So the one, just give you some flavor about the different machine learning applications. Just pick one for each. The first, most successful neural network is for the handheld digit for postal office. So in postal office nowadays is already in production. All your letters can be scanned. The zip code will be recognized right away because they have this nice neural network that detect the digits in the certain area. So the way you do is you divide the region into different pixel regions, and each is one input node, and output is your desired class. So for digital recognition is 10 class, right, from 0 to 9, and you take the areas of the letter. So this is, and you can do neural networks with many other tasks. For decision tree, I want to show one application is basically in the known application. We look at the person's checking account, saving account, the credit history, and other informations, and then you make a decision on whether give a loan or not. For SVM now has a very heavy application in spam filter. So in spam filtering, you basically these are the information you can use to build the classifier. You say, where does this email come from? What's the sender's IP address, the URL or other information? What's in the title? What's in the header? And then what's in the email body? So all these are part of the features you feed into a classifier. Then you can build a SVM classifier.
What are
Yes.
some popular techniques to turn text-based features into forms that SVM can make?
When we come to text mining, right? So essentially, it's the techniques is part of text mining and natural language processing. So that's you process the data and then convert that into a feature to use. So for example, term frequency, right? So certain term frequency, that's one way to convert a text feature into a binary feature, into a numerical feature. So essentially, for SVM, the input has to be a number. It has to be a numerical number. And the numerical number is best from 0 to 1, so you normalize a number. If it's greater than 1, you normalize the whole column between 0 and 1. And essentially, you can get, so everything is number. There's no text anymore. We talk about logistic regression. Logistic regression is mostly useful for like a click prediction. That's why internet company really likes it. Is would this person, if I show the search result, if the search result is good, people will click on it, right? If I show the search ads, when they click it, I would know that my ranking is good. So the outcome is a click or no click, and then I can train, build a click model, click prediction model, and then to rank my product, either do product search or web page search or advertising display or many other places where the click is the feedback, the outcome.
So is it fair to say that you use this for places where your output is binary?
Your output is binary. You can, I think, you can. That's your question, right?
Yes.
You can do multi-class logistic regression too. Yeah. Yes.
Is SVM also good for click prediction?
Yes, you can. Yes. For prediction model, any classification method can be used. Even decision tree can be used. So there's no. There's no special thing we have to use the logistic regression for click prediction. But the nice thing about the logistic regression is it also comes a way to do feature selection. So That's much deeper. That's basically newly invented in 2000. People use combined logistic regression with we call that L1 norm regularization. Combined together, you can throw in an optimization process that you can automatically select the best features. So logistic regression gives you that power to do feature selection combined with classification. So that's why people use it. Yeah.
So SVM and logistic regression, which one is more parallelizable?
Logistic regression is easier to parallelize. All right. So now we come to clustering. So I want to just briefly mention 4 major clustering methods, and you can see from the shape of the end result that basically give you a high-level view the difference between these 4 different methods. We typically say k-means is a spherical clustering method because you use the distance from centroid to the external. You basically use the centroid to measure the distance. So essentially it's a ball. It's a circle or ball if it's in the 3 dimension. So it's always a round shape. That's k-means. K-means is nicely applied to those kind of situations where you can have a round shape distribution on the clusters. However, certain cluster, like in the expectation maximization method, where they may overlap. It's not a necessarily round shape. Maybe it's like ellipse, where the main difference. So you can basically in this kind of clustering, you are basically measuring the mean and the variance of 2 clusters. So they have different mean and different variance, and then you basically have you are trying to optimize the separation between these 2 clusters. So that's expectation maximization. Now in density clustering, we allow any kind of shape. So the way people do density clustering is we look at the for any given point, we look at the density, how many points are allocated in the near region of that point, and that form a cluster. If there's another group also densely allocated next to this group, we combine them together. So you can grow the cluster here into arbitrary shape, as long as they are all dense connected together. So then this is actually very powerful when you try to classify certain data that has no pre-given separation. For example, like in the stream data, we don't know what the cluster will look like. So user density clustering is easier for us to give us flexibility in that sense. The last one is hierarchical clustering. Basically, you merge 2 points, the most closely together. So you do pairwise. You pick up every pairs and merge them 2, and then go 1 level above. It's very tedious. I think it's very time-consuming to do hierarchical clustering, but in certain domain, maybe still useful. The applications mostly for malware detection. For example, nowadays there are many different kind of malwares. Some are executable files, some are just phishing, some are sending information out. There are different. So how do you classify your files, even all different malwares, into different types? So that is a clustering because they change every day. There's no given. Even though some experts try to classify malware, but next month or next year, the class would totally change. So that gives you a way to do malware detection. Intrusion detection also the same. There are many kinds of intrusion detection. There is denial of service. There is unauthorized access, trying to guess the password. There are other ways to attack your network. So how do you group those instances together? And sometimes it may be normal. There's normal activities. So that requires clustering. Finally, the document clustering, certainly it's for marketing, for understanding news, understanding what people talk about. So the third method I've mentioned, so from supervised learning to clustering to frequent mining, I mentioned frequent pattern mining the last because it's not used so frequently nowadays. It's still used, but it's not as powerful as a machine learning method because machine learning actually allows you to adapt your model to new data. Frequent pattern mining fundamental concept is you try to count the frequency of a certain purchase or certain co-occurrence of different items. So for example, suppose I have 1, 2, 3, 5 items for sale. In my sales record, I can count the count of individual item. And so one algorithm is I remove the infrequent, so that speed up my computing, right? So I remove the number 4, because it's only purchased once. I don't have to care about its correlation with other items. Then in the 2-item set, I then sort them by frequency and then count the higher frequency ones, and then go to the 3-item combination. That is just cut down the computation on higher dimension combinations. So in the Amazon case, in order for them to say, here's the frequently bought together, think about how many merchandise they have, right? Think about how much computing they have to do very quickly, almost every day, sometimes every hour. So in order to speed up this kind of computing, give you this result, there are a lot of research has been done to design a faster, frequent pattern mining algorithm. So there are several algorithms, classical ones with some new algorithm, but I won't go into detail here. But basically, essentially, is first of all, you have to scan the whole database and counting the frequency. Now, do you have to scan it again if you counted the combination items? If you don't scan it again, how do you store that in the storage, right? It's going to be huge storage requirement. So all those problems comes in as a computer scientist worry about those problems. Yeah.
Sounds a little risky to me because if you're eliminating the low frequency bought items, maybe that is the driving force for you to buy other things. Like for example, unless you buy a bed, you won't buy a mattress,
yes.
pillow, and all those things.
So I understand your concern, but think about it on Amazon. How are they going to show the low frequency ones because they don't have space, right? So if I have 1,000 item I can show to the user, I should always show the top ones, right? So that's the fundamental. So that's why they say frequently bought together. Other people also bought this, so they sorted by frequency.
You may also put like pricing account. Let's say a bed is actually a high price item, so you can sell it at a low frequency.
Right, yeah. Yeah, that goes deeper beyond the frequent pattern mining. That's more like optimization. So there are people who work on optimization, the whole like profit optimization criteria. All right, so the third, moving from the 3 fundamental technology, I want to maybe, given the time, want to mention 2 or 3 domains and some case studies that I basically showed earlier. I just want to quickly give you, let's review that slide. So I'm following this slide. We mentioned the top 3. I'm going to recommend the system now, and then I basically give you a couple examples, and then talk about some application in network data. And I will, for today's talk, I will then mention some examples of the text data, text mining. recommender system used by Netflix for movie recommendation. Sometimes even in Amazon, there is a recommended for you. There's some special recommendation page in Amazon. So Amazon does recommendation too. Instead of doing frequent, on top of frequent pattern mining, they also do personalized recommendation. So traditionally, the recommender system is called a collaborative filtering. So the idea is I can use other people who are similar to this user to make a recommendation. So that's called a collaborative filtering. And so, for example, if you look at user similarity, like basically say this user rated this movie as a 5-star, they are similar to each other, they always rate higher of the similar type of movies, then I can predict this user will also rate 5-star. That's user similarity. Item similarity is just turn the things around. If you look at Netflix, they have 20 million users. They have 100,000 movies, right? If you do user similarity, you have to do 20 million pairs of comparison. So the distance between this user to 20 other million users. So computing is huge. So to cut down the computing, people actually say, can we look at item similarity? If these two movies are very similar to each other, have a similar group, I can actually automatically predict this user's rating for this movie by going with the column instead of the rows. So item similarity is a way to cut. Same thing for Amazon. Amazon is using item similarity. The third method is look at the whole user item rating matrix, decompose that into a latent factor, where basically each movie can be represented with small number of factors like director, genre, the movie actor, and other information to represent the movie. And also the user preference can be represented by their gender, age, or other information. So essentially you can decompose a very huge matrix into smaller matrix to understand, to predict their preference. And so, but today we moved beyond the collaborative filtering. What I'm trying to, not in this talk because we don't have time, but essentially what I'm trying to show that nowadays the new recommendation system move, even including Netflix, they move away from collaborative filtering into more ranking-based model. So the way to make a movie recommendation is actually just calculate the score ranking on different movies for this user, and then sort them by the highest scored movie. Now the reason ranking is more popular is before we only care about the ratings, the user's opinion, but now you use implicit feedback like the clicks, how long they stay on the page, what genre they have browsed, how often they come to the site. So there are many implicit information you can capture about the user behavior. In order to capture that behavior, you need a function that basically describe about this user that cannot be condensed into a collaborative filtering framework, which is much more difficult.
Can you give examples of what machine learning algorithms they use for rank based?
It's the four methods I talked about. So SVM, they use SVM, they tried decision tree too, they did a logistic regression. So essentially when you do machine learning, you test all these methods and see which one works best. There's still company coming out of the collaborative filtering domain still use it, and they show that it's very successful. Actually, it's more successful just comparing to item similarity to user similarity. Like the latent factor model is more powerful than the traditional item similarity. So they have this company, a startup, is a mobile one of the largest Android app marketplace. Basically, they can make a recommendation to you on the new app to use. But if you look at more modern recommendation system like LinkedIn recommendation system, they all use a ranking base. They don't use collaborative filtering. And so they build a ranking score on different jobs, on different groups or different news, and then they sort them. Alright, so now I want to move into graphs very quickly. I'm using up almost the whole hour. So graph model is basically in the natural world, in our society, in the commercial setting, is actually very widespread. If you look at from drug design to the social network, also to like a warehouse, like Amazon delivery, the Amazon warehouse is a network, right? Which if they want to send you your purchase, which warehouse should they send from? How do they reduce the shipping cost? So those are very actually practical problems they face. All these graphical mining problems. So one of the application this is a case study we will talk about in the future, is how do you understand who are the top influencers on Twitter? The reason for that is for marketer, for public PR agency, you do want to know who influence other people's opinions so that you can reach out to that person, or you can identify who lead the discussion. So in that, you basically we can build a graph model on the Twitter between users who follows who, and then calculate the importance of every node. It's like calculating the page, but based on certain topic. Like, for example, if PayPal care about customer opinions, so everyone who mentioned the PayPal, we can sort them, look at who is the person really care about influence other people more when they talk about this topic. How many of you have used the Facebook graph search? One? Okay, yeah. How was it? Is it better?
Yeah, it's better.
What?
Well, it's limited.
Why?
It's better but limited. I'm not sure if they have. There's a specific path. It works well, but I'm not sure they accounted for vague areas.
Right. I also found that it's a conditional. What my friend actually talk about, right? If like for a restaurant recommendation, I have a couple of friends always talk about a restaurant. Many other people never talk about restaurant, right? So that, yeah. But what's nice is they can give you this entity-based search. Say, instead of just search for a restaurant in the nearby area, you can connect the restaurant to a friend through this more network graph. Then I can search, they build a search technology that can search for entities. So that's very nice about the graph mining. All right, so we are almost done. I have 2 more slides to show. So here, for the text mining, just give you a brief overview of the technology. Basically, for generic information retrieval, people use term frequency, inverse document frequency. For more NLP approach, we do stemming, basically take the word, discover the original form. Instead of swimming, you can swim, that's a stem of the swimming. So that removes a certain redundancy or variations. Secondly, you can do part of speech. Part of speech basically means noun, verb, adverb, adjective. You can classify every word into one of the part of speech tag. That'll give you additional information about what the people talk about. Right. Thirdly, name entity detection is detecting like the company name, person name, drug name, the email address, phone number, product name. So those are the entity detection, which becomes very actually popular. I know several startups started on this. There's a legal company I mentioned in my blog that they look at all the patents and they use entity detection to search for patent document, right, and find out who is talking about which patent already been filed on this subject.
So we should know that something is a name because we have across cultures different naming nomenclature and stuff like that. So how do they know that it's a name and not a verb or adjective?
Exactly. So it's very difficult problem. It's not easy to do simple keyword matching. That's why we say it's part of NLP technology. It's for example, red. Red can be color, but it can be brand name, can be a company name, can be many things, right? So just doing keyword matching doesn't work. You have to use context. You have to use maybe historical data for other from other information to show that. The parsing is basically convert a sentence into a structured format from subject to subject, object, and the verb phrase. So that gives you a structure of the sentence. So one of the application, I know also several startups now actually are working on this. They crawl the internet, try to build a search shopping engine. So all of them have to solve this problem. Is suppose you crawl different shopping website, and how do you put together different products? So that involves the attribute extraction, product attribute extraction. So we're given a listings, how to identify the brand name, garment type, color, size, and I said there are many ways to talk about the size, right? So even, so there's 3 words here, but there are always XX small, XX dash. So there are so many variations people can talk about. So that is very challenging for. All right, so I won't be able to cover every domain today, but this gives you a flavor about what data mining field basically is talking about, what are the potential business cases. If you have more questions, feel free to contact me, send email to me, and next time I'm co-organizing this event with the Friday evening machine learning discussion group. So I will talk about the case study on text. So next time we will talk about text mining, and hope to see you. All right, thank you.